My name is Shehroz Khan. I did my PhD with Dr. Jesse Hoy in CS, and a lot of my focus was in developing fall detection algorithms, but we were looking at wearable devices and all that, and the focus was more on the algorithm side, and I started my postdoctoral research at Toronto Rehab and UFT, currently with Dr. Alex Maladis, and I'm working in Toronto Rehab. So how many of you know about Toronto Rehab? Okay, so that's a lot of people. Good. So Toronto Rehab, for those of you who don't know, is Canada's #1 rehab institute. It's a hospital. It's a great place to work, and basically the top floors of Toronto Rehab is dedicated to research, and you see a lot of multidisciplinary kind of work, transdisciplinary work going on there. You see, I work with psychologists, doctors, computer science people, engineers. Which is very different from what I was doing here. I was just sitting in my room, and everybody is CS, but it's so interesting, and we are exposed to so many interesting real life problems. So I'm working on many projects, and we can talk a little bit after my presentation. But one of the projects that we are currently working on, and I'm leading this effort, is this fall detection, but very different from what I did in my PhD. It's a totally new domain, I would say. We are using different sensing modalities, totally different population, different ideas. So I'm going to talk a little bit more about that. And just before I start, I want to have a sense of the audience. So I know we have some people from CS, we have people from engineering, right? Other areas, Sorry? Public health. Okay, good. All right. So just wanted to have, because I don't want to go too technical in this talk, but we can talk about it if you want. All right. So the title of the talk is Non-invasive Fall Detection Using 3D Convolutional Autoencoders. So like as I was saying, there are different ways we can look at this problem. And wearable devices is one of the things that have been explored. I also did that work in my PhD, but now we are moving more towards non-invasive, non-wearable kind of approaches and how they can work in the real world. So why fall detection is important? I think everybody in this room has fallen at least once in their lives, and we know that it is not a pleasant thing. It looks good for young adults, healthy adults, until you do not break your bones, until it's not dangerous, but falls are dangerous. And according to the Smart Risk report, falls comprises of 25% of all the unintentional injuries and 50% of all the injuries that resulted in hospitalization. And according to Public Health Agency Canada, older people are at more risk of fall. And this is more due to their frailty, weakness, all those issues. And falls are deadly. I mean, they can cause severe injury, could lead to death, unfortunately. And apart from that, there are direct healthcare costs involved with it. Very conservative estimates suggest billions of dollars are being spent on this. And apart from that, there are several psychological effects related to fall. So you may develop negative physical, mental consequences, long-term care, fear of falls. You may develop that may lead to lack of social participation and lack of activities. That is even actually worse for you. And as you get older, this happens. Like I'm actually seeing that one of my aunt actually she fell down and broke her hip bone, and they had to put in a rod, and after that she's very scared to go out. She doesn't socialize, and that is actually not good for her. But that's the reality. So how fall detection is performed, just to give you a rough idea, you place some sensors, either they are like as I said, wearable devices. It could be some vision-based system. You put in some cameras, or you can put in some ambient sensors, pressure sensors, whatever type of sensors you have. And then you apply some techniques. So very simple techniques could be like thresholding kind of techniques. You have sensor data, you put some threshold and say, oh, if the sensor value go a little bit up or low beyond this point, then it may be a fall. Or you can do some binary or multi-class kind of classification, machine learning kind of classifiers, that you have a classifier for fall, with normal data. You train a classifier with normal data, fall data, and then it looks easy on paper in theory. However, again, another reality, like there are different realities. That's another problem. So, so the problem is that falls occur rarely. We do not fall all the time, right? It's very infrequent. It's very rare, and but we want to detect when we fall down. And there are some long-term studies, most notably by Stone and Skubic, that they actually collected 13 years worth of fall, data in long-term facilities, and they found like I think 10 or 15 falls, which is actually very related to another statistic that comes from Center for Disease Control and Prevention. They say that in the long-term facility they get like 2.6 falls per person per year. So to give you a context, if you put a sensor on, let's say, my body or anybody's body, and you monitor an activity per second, so that will be like around 31 million normal activities over a period of 1 year, and you get 3 falls. So how can you build a classifier with this kind of massive skewness? It's very hard, right? So to circumvent this problem, what researchers do, they collect artificial falls, which is okay to understand the mechanism of fall, but there are studies which also suggest that they are not true representative of fall. And from the machine learning perspective, they may lead to overfitting. So you may be just learning a particular types of fall, but not like the general idea of fall. And apart from that, from my personal experiences as well, there are several issues with data collection. You have to be very careful. You do not want your participants to break their bones and go to hospital. Ethics is a major issue. We were talking over the lunch with Jan in detail about the ethics issues in some of the projects that we're working on. It can take years and years to get ethics clearances. And then privacy issues, like people don't want to be monitored by cameras. People are very particular about their privacies. And then invasive, whether these sensors are invasive or not. So the hypothesis in this project we had was, can we identify falls by training models only using the normal behavior in a non-invasive manner? Okay, so why only normal behavior? Because this is the data that is present in abundance. I can collect lots and lots of data for normal activities, but I may not have very few samples for the negative class, which is like the falls in my case, right? So how can I do that? Speaking of which, from the non-invasive sensing side, I would like to spend a minute on this thermal camera. How many of you know about thermal camera? Okay, good. So that's pretty good. It's nice to be with engineers. They know everything. So am I even required here? No, it's really good. So you know that how it works. It uses your body heat and infrared to form images, and most of these images tend to be monochrome. And traditionally, these thermal cameras, as you already know, they are wall mounted and handheld. They used to be very expensive, and they were used in very specific applications by firefighters and people who were looking for localizing the heat leaks in your buildings and stuff like that. But now we have you can get a attachment for like a hardware dongle for I don't know $200-300. Put it to your mobile phone, and your mobile phone can work as a thermal camera, which is very cool. So then thermal cameras never come into the mainstream research because of the cost thing, but because of these latest advancement in hardware, we see some of these applications. In fact, there has been some interest in fall detection application as well. So as probably you might have seen, so now you can like put this attachment to your mobile phone, and you can see people. Like in this picture, you can see this lady, but you cannot clearly see her features and everything. So you can see, but you cannot see. I mean, it is debatable, but from my perspective, you are sort of preserving the privacy. You can see what the person is doing, but you may not exactly see who is that person, right? So you can collect a vision type of data, but in a more anonymized manner. Okay, now coming back a little bit towards the technical side of the things. So like as I said, we were having a problem with this data collection. We did not have many data for false. So one of the way to do is to look from an unsupervised learning perspective, and autoencoders are a good candidate for that, because autoencoders are unsupervised neural network models, and moreover we can learn some features that may help us in actually identifying the false, or at least the not normal case. So in an autoencoder, typically what happens, without going into the mathematics of that you have some input, okay, and you want to reconstruct the input. So in an autoencoder, you give your image as an input, for example, and you want to reconstruct it, but you want to enforce some constraint on it by, let's say, reducing the size of this layer. This is called the hidden layer. You can have more than one hidden layers. And the idea is that this is the loss function that you want to optimize, which is basically the mean squared error of your output and input, input and output. And so the idea is, if you can reconstruct your input pretty well given these constraints, then you are successful in achieving some compression of information, right? So I'm reducing the dimensionality, I'm encoding, and then I'm decoding, but the reconstruction is very small, let's say close to zero. So it means that this representation is very informative. It is compressed information, but it is very informative. So traditionally autoencoders are used for dimensionality reduction. They are used, you can learn class-specific autoencoders. You can use them to pre-train the deep networks and do the anomaly detection. So this is the approach that we are going to utilize in this work. And in anomaly detection, again the idea is very simple. The idea is that if I train an autoencoder on a specific type of data, okay, and I optimize this function, so the reconstruction error will be less. So if I give you an object which this autoencoder has not seen before from a totally different category, then the reconstruction error should be very high. And based on some threshold, I should be able to flag this. That's the idea. So I mean, if you just show bottles to this autoencoder, so it will learn on different types of bottles. We have 5 types of bottles in this room, right? So we can learn. But if I give input as this, as a mobile phone, then the reconstruction error will be very high, because the autoencoder is trained to identify bottles. So that's the simple idea behind this autoencoder. To give you some more idea about how this works, so what they did is they actually trained these autoencoders on different tasks. So one of the tasks was handwritten identification. So this is the original handwritten letter 2, and they applied this autoencoder and they reconstructed it, okay. And this is the compressed representation that I was talking about. And based on, so you can learn different filters. And these are some of the visualization of some of the filters that they learn. And this is the idea of deep learning, that how do I know that this is a bottle? How do I know this is a computer? Because I think this is a hypothesis, nobody has proved it yet, that we learn information in different hierarchies. So maybe different parts of our brain are learning like small features like arcs, edges, and then maybe combination of there to form more complex images and things like that. So these are the different filters that an autoencoder learned when it was trained to learn these digits. And you can see these are very fine strokes. These are the strokes. These are the combining strokes when we form these letters. And the autoencoder was actually successful in, I don't know if you can see, in actually learning some of the digits itself. So 7, 6, 8. So this is very interesting how these autoencoders can learn information. Okay. So, however, there are certain limitations to this approach. One of the thing is that, as I showed you in that original image of autoencoder, it requires a vector. And we are talking about images here, especially this thermal images, right? Images of people. So autoencoder ignores the 2D structure. It requires like a vector kind of thing. So you lose that information. If you're working with images, you lose that information. And autoencoder learns global feature, like it only sees the picture as a whole, but it doesn't look into the specific parts of the images. So to do that, we will use convolution autoencoder. So probably you might have read in your engineering classes this convolution operation, and the way it works is, if this is your image and this is your kernel size, which is jumping, and you're going stride by stride. So you can learn some filters, and you can learn different types of filters from it. Like this, you can do some zero padding of around the image. The stride is more. So different types of filters we can learn. I mean, just imagine there's a like an image of a person. So you can learn some different spatial sort of filters. And the good thing about these filters are they are translation invariant. So if I show you the bottle like this or upside down, it should be able to learn translational and rotational invariant features. Okay, so we can use this idea of convolution autoencoder to build convolutions to build a convolution autoencoder. So as I said, we should be able to learn translation and rotational invariant and the invariant features. And the good thing is that it preserves the spatial locality that irrespective of the movement or the shear you apply on the, I can twist this bottle, but still it is a bottle. So it can learn those type of features as well. But again, the problem is whatever you are learning, these are images and these are spatial images. But what we are talking about is not just a spatial, like the thing that is present in the space, but it is moving in time also. So imagine me, you have a camera, a thermal camera, watching me, and if I'm walking, then I'm not just making different poses, but I'm also doing something in time. But these convolution autoencoder are not capable of learning these temporal features. So to do that, we use these three-dimensional or 3D convolution autoencoder. And what we do is that instead of applying this convolution operation on one image, we make a stack of images, and we try to so this convolution is just not a cube, but it's not a rectangle but a cube. So I'll show you a graphical representation. So this is the 2D convolution that I showed you, that GIF image that I showed you. So you have this image, this is your filter, and you learn these convolution filters. In the 3D convolution, you have different images stacked together. So you basically capture some temporal aspect of it, and your filter is not a rectangle anymore. It's a cube. So you are actually learning some temporal features as well. So that's the basic idea. I'm not going to go more detail after this. This is the end. All right. Okay. Now, before we move forward, I'd like to give you some idea about the data set that we are working. So we are working on different types of data set. This is one of the data set that was actually collected by Verivalue, and I'm very thankful to them to share their data with us. So they use like a Android phone like this with a thermal this hardware thing that turns your phone into a thermal camera, and then they collected a lot of these activities. These are actors. These are not real like patients or real people. I mean, of course, this is he's a real person, but he's a real person, but he's an actor. So in the data, we have many empty frames. We have some frames where the person is doing few things, normal activities. In some frames, we have a person entering the scene or exiting the scene. So this is a very challenging data in the sense that we have different types of things going on. And if you can see, resolution is also, the background is also very different. Some of them are more darker than the others. So it's not a very process kind of data. Okay, so and it has it consists of 9 activities of daily living videos where a person would do different types of activities: sitting, walking, whatever, walking with a walker, sitting on a chair, sitting on the floor, these type of things. And then they have 35 short videos. So these are pretty long videos, and then we have 35 fall videos where a person would come, enter the scene, and would fall down. Okay. All right. One last picture, and then we are done. All right. But yeah, huh?
You said that before.
Yeah, I'm sorry. I'm just kidding. So just to give you some more idea about how this 3D autoencoder actually works, in principle at least. So your input is not one image, but a stack of images. For our task, we take like 16, I think 8 images. So the input is like a stack of 8 images, in time. And then from that you learn, you apply these filters and you learn these different 16 filters. You reduce the size because these are 64 by 64 images. Okay, the original size was even bigger, so we resize these images to 64 by 64. And this is always challenging, like what should be the size, because we also have limitation of the resources, even though we are running these programs on SharkNet. But again, this is always a challenge. Like it takes a few hours. Like 3D convolution literally ate up our computers. Like 2D conv I could still run on my laptop or on my PC for a few hours, but when we started running this 3D conv, it's just end of everything. So we had to go to the SharkNet and we had to run these codes there. So they are very intensive, computationally intensive. So we need to understand this aspect as well. So then we do max pooling to reduce the size from 64 to 32, and then we apply this multiple times. That is why it is deep. And the idea is that we went through 3 levels, and the idea is that we should be able to learn different types of features, different hierarchies or abstraction of features. We did this few times, and then so this is the encoding part, and then the decoding part where we try to reconstruct everything back. So this is your input and this is your output, and it's pretty good. I mean, it works pretty nice, and I'll show you a demo, and it's I think it's quite impressive. Okay, so this is a 3D deep conv net. So how do we detect fall in this? So one of the challenge was to annotate the data, like how you're going to test it. You can come up with all these fancy ideas and great algorithms, but again, so I think this postdoc had a very humbling experience. A PhD was like, oh my God, I'm going to change the world. But first of all, I have to change myself, I think. So I think so. In my PhD, of course, I did a lot of data pre-processing, but most of the data that I used was actually collected by somebody else. So I just went there and downloaded it, and it's all right, everything's fine. I was more focused on the algorithm side. But here we are doing everything on our own. I mean, this is not even like real data like that we are planning. I'll talk about it a little bit. But in another study, we are actually collecting our own data, and that's such a nightmare. We have to do all this, annotation. Before annotation, you have to come up with a strategy. How are you going to even think about this? And you have to do it on. And there's a lot of man hours that you spend on this. So I think it's a very challenging and humbling experience. So we had to actually so these videos were not labeled. They were just they collected, they uploaded it, and like, yeah, go, you're on your own. So we had to actually manually annotate these videos, especially the not the training ones, but the testing ones, the ones which had falls in it. So we had to come up with a strategy to sort of manually annotate those videos, because otherwise how are we going to test it, right? And then the idea is to train this 3D convolution autoencoder on only the normal activities, which comprises of empty frames, which comprises of a lot of walking activities, sitting, whatever the person is doing, and a lot of these where the person is only half available, entering, exiting kind of thing. It's so hard to like segment all of these. So we just let the autoencoder learn on everything and then see, okay, let's see what happens. And of course, like the idea was to minimize the reconstruction error on the input image. And for testing, what we did was we gave this test video to this image. We had the ground truth, okay, and we measure this reconstruction error. And the idea is if it is a fall, then we should see major deviations, and they should be, and those deviations can be identified as fall. So excuse me, I'll take a break. Okay, so that's the best part, like demo and pre-recorded, so I'm sure that it will work. Yeah, demos don't work most of the time. So, so this is actually a demo of whatever I've been talking about for the last 20 minutes, 25 minutes. You will see an original image. I can actually start because the person will enter the scene quite late here. So this is the original image that is fed to the classifier. The classifier has not seen this video before. It is only trained on normal activities. This is the reconstruction. This is what the 3D conv is reconstructing frame by frame. This is like a numeric measure of the reconstruction error. So far, it's reconstructing it well. So it's pretty close to 0. It's not 0, but it's pretty close to 0. And the person will enter soon, I think in 5-6 seconds, and then come on, yeah. So now he's entering. They made so you see the reconstruction is a little bit up now, okay, and then he'll walk around and then he will fall down. Bang, all right, and now he will rest on the floor for the rest of the video. So this is very interesting because of a few because of few reasons. First of all, we haven't seen this video before, right? So it is very challenging to understand what's going on. When this was the empty part, okay, so it was able to reconstruct it pretty well. When the person entered the scene, the reconstruction was not that great because of so many artifacts. There's furniture, there's a fridge, so many things are there. And actually, the 2D conv autoencoder did not work well because of this problem, because it was trying to reconstruct the fridge, the chair, the bed as well. But the moment we incorporated temporal information, it started to learn the temporal features as well, apart from just the background and lighting and these kind of things. And we see a sharp rise in basically the performance. So I'm just showing you the best results, but but you see, and when the person falls, I mean, this literally shoot up. So we can clearly see that something is going on here, and this was a fall. So, and I have another video which is I call as the average case scenario. So this video that I showed was like a really good video, which is like a perfect case scenario. This is the average case scenario, and this can have these kind of, okay, so you will see. This is again, so initially this is 0, and I think he comes around here. Right, so he's going to enter, and certainly the reconstruction error is very high, and I'm going to talk about why initially it was so high. And then he sit there and come on, and then he falls down, right? and then he keeps on falling and nothing changes after that. So we see two sort of peaks here, right? And this can be deceiving, what was going on here and what was going on here. And this is sort of a, I would not say consistent, but this was occurring in a lot of the videos. And there are two explanations for that. First is, when you're entering the scene, sometimes your only head is visible, sometimes your one hand is visible, you know, sometimes your half body is visible. So maybe the network is not trained well enough on these type of images or these type of videos. So maybe the reconstruction is not that great. That's one aspect of it. And the other, I think, thing is that it could be due to different setting or arrangement behind, you know, it could be different lighting, it could be other things that are contributing to it. But nevertheless, in almost all the videos, we were able to actually get a high peak for falls. So even though you are getting multiple peaks in reconstruction error, you can still, you know, go back and look, but falls can be distinctly identified. I mean, this is the message that I want to give here. And you may still get some other peaks because of other artifacts of the environment, but you are still able to detect falls. And we have not, and especially this is remarkable because you have not seen this thing before, you have not seen this behavior before, and the network is still able to identify. Okay, so from where we are going forward with all of this that I have been talking about. So we have a home lab. Has anyone been to Toronto Rehab, like inside? Okay, you were there, I know. Okay. Yeah, these are your pictures actually. In one of the picture, actually, you are there. Probably. Yeah, like you're making notes. I hate that picture. Yeah. So you've been there, right? So have you seen home lab? Right, great. So home lab is actually it's like an apartment kind of thing that has been built where we can do all these experiments. It's a very nice facility. If you get a chance, go, come there and have a look. So we can do a lot of these experiments in a very naturalistic kind of setting. So one of the thing is this fall detection system, which is already installed there. So it has a tiny camera. It's mounted on the ceiling, right? So this system is already there, and it uses, I think, some computer vision old techniques. And what we're planning to do right now is to improve that system and enhance the capabilities and add more types of sensors in there, so that we can. So here you can actually simulate life in a apartment, or that kind of thing. So this is a very nice facility. Okay. So the idea of this fall detection system is that you have this unit or maybe multiple units, mounted in your apartment or in your house, and then if you fall down, then you can do. I mean, the system can interact with you and can ask, how are you doing, John? Or are you okay? Did you fall down? You can talk to the system, and then based on your communication, it can decide whether to call for a help or something like that or not. So this is like going forward. This is what we want to do. In terms of future work, I think the target population that we are focusing, older adults, and especially with cognitive disabilities, dementia. I think these are very challenging and very difficult sort of group, because their behaviors are very different, especially people with cognitive disabilities. Their behaviors are very different from normal people. They cannot explain their issues. They cannot tell if they're feeling weak or bad, if they're agitated, if they're angry. Sometimes you may just run, for no reason, because we work with people with dementia, so I know, they exhibit very different kind of aggressive sort of behavior. So it's very hard to know how they're feeling. So I think it's very challenging to tackle this population. Apart from that, from the technical point of view, I'm very interested in looking into other temporal kind of models like recurrent neural networks, these kind of things. And then in fact, we were talking over the lunch that how how do we monitor multiple people in a scene? So this was just one person, but if you have three people in there, the system won't work, right? And how would I know that this is the person of interest? The person can have his family, but you don't want to monitor their family. You just want to monitor that particular person. So how are you going to do that? I think this is a very challenging thing to do. There are something. There's a award-winning actually paper in the CVPR last year. It's called YOLO, Y-O-L-O. You only live not once. You only look once. Yeah, that was the title of the paper. You only look once. So I have actually used that, and I think I installed it on my laptop as well. So it's pretty good in actually tracking people, identifying objects in real time. If you have not seen it, I mean, go watch. I think it's on YouTube. It's phenomenal. It's impressive. They actually can identify different objects in a scene in real time. So that could be one way of doing it, but I don't know. So tracking person, individual person in a scene is very important. And moving forward about the sensing modalities, we are more focused on this non-invasive, non-wearable type of sensing modalities. So like depth camera. So one of the PhD student in our group, he is working on depth cameras, and in that picture that I showed you about the home lab, we have actually installed the depth camera, and we are also looking at radar motion sensor that you can just put it wherever on your walls or in the ceiling, and you should be able to capture some motion data, and there are some clinical actually studies that have been done for fall detection with radar motion sensor. It seems to be a very interesting sensing modality, and you don't have to wear anything. And radar is even better because you don't capture any image. It's just motion, and it can see you through walls. So even if you're outside the room, it can still monitor your motion patterns. So we're very excited to actually collect data from that device as well. I think it's ready for data collection, and hopefully in 2 weeks or so, we will be collecting some data in-house in the home lab with depth camera and radar motion sensor, along with RGB, because we are not totally ignoring RGB. So basically the idea is to monitor the same thing from the ceiling, but 3 different sensing, 3 different modalities. So idea is to fuse these sensors in future, the information, the different types of information, and probably use this kind of approach that we have been developing. Other issues are more, from the deployment perspective, but I think it's good to think about them early on. And one of the things that I noticed, that I feel, is this real-time prediction latency, because these systems, you want to deploy in real time, right? And they have a latency. So how much latency is good or bad? Like you want to tell 1 hour after a fall or 1 second or instantly, but instantly is not possible. So how should we decide that? Because life of a person can be at stake. So these are, I think, the challenges that we have right now. And yeah, so that's it. Yeah, this is this is a random picture. So in this autoencoder thing, we learn a lot of filters. I showed you a picture of filters, and I've been just thinking about filters a lot, that I'm seeing filters. So this is a art installation, I believe, in some mall in Toronto, in Vaughan Mills to be specific. And when I was looking at it, I saw it as a filter, But can you see what it is, right? Right. It's that though, locks. It's locks actually. So for some people it may be superstition. You put you log and you make a wish, and I don't know what it is, but for me it's a filter. Yeah. All right. Thank you very much. Thanks for listening, and I'll be happy. Yeah. So this is a very good question actually. And I'm glad that you noticed that. The reconstruction error, for each video is actually, yeah, so for each video it is sort of different. So for now we are analyzing each of these videos differently, but I think finding the exact threshold is very hard. This is actually a major problem here. So the way we are evaluating right now, we are doing this AUC, area under the curve. We plot a ROC curve, and then so we're trying to find the performance at every possible threshold, like all the theoretical thresholds. But you're right, when you want to deploy it, you need a specific value, right? And this should be consistent across, and I do not have a good answer for that, like what should be the right value of the threshold at a from a global perspective. It's very hard to say at this point, but we understand this problem. I know that this is a problem, and during my PhD also, like I try to tackle it in a different way, but those ideas cannot be used in this vision problem. But yeah, finding like a right threshold is very hard. Yep.
Yes, I was also a little surprised that you're basically doing no pre-processing, right? You just downscale the images. So why not at least add like background subtraction?
Yeah, we did actually. Yeah. So there is a bit of pre-processing. So we resize the image. We remove the like the intensity, the mean intensity, right? So we do 2-3 types of processing steps. But background subtraction and all that, we did not go in that direction, because that is again, that there are different ways to do that, right? I mean, you could do that in principle. In fact, for this data collection that we are that we are planning, for that we try to find like a representative image and then subtract this image from the subsequent images to sort of remove the artifacts because of light and the furniture and things like that. So we do a little bit of we will do some sort of pre-processing. It's actually a good point, because it's very hard to use. Those images may not be very useful, right? Yeah.
When you start using 3D data, like are you still going to be using temporal? Like won't that get really big to process just because you're adding a whole other dimension, so it should increase audio processing by a certain amount?
Yes, the number of parameters actually increase, because it's just not the input. All the filters that you're learning are now 3D. Okay, so the number of parameters actually increase a lot, and if you're going deeper, so if you're using 2D conv autoencoder, everything is an image or some sort of image. But now you have an added dimension, so everything actually blows up. So that is why it's very computationally extensive, right? Sorry.
Like when you're planning on moving to 3D cameras, is that going to make it like impossible to compute? Like almost like just because if you're starting to do temporal, like you're going to have
on a 3D camera?
Well, that's what you're talking about doing, right? Like stereo with 3D cameras.
Not really. No, not really. So these are just ordinary cameras. The images that we are getting are just like 2D images, right?
Yeah.
And we just stack them together, like 8 frames together.
Sorry,
right.
About the future work with the depth camera.
Oh yes, depth cameras. Okay, all right. Sorry. Yeah, no problem. So yeah, depth camera is actually very challenging. Depth camera. At this point, as I understand, we will be analyzing in a similar way. Because another data that I did not talk about in this talk is also a depth, and it's available online, and we analyze them in the same way that we did for the thermal images, and the results are pretty decent. Like for the thermal image, the results are very good. For the depth images, it's a little bit difficult, because the shadows. There are other issues there. Shadows and if you have different objects, they can be perceived differently. It added its own complexities, right?
Yeah. So yeah, in terms of the computational complexity and like robustness to different environments and settings, right? It seems like the amount of processing power
As far as I understand, skeletal tracking is very like mature and like good, right? Like you can easily track human skeletons
Oh
from the
yeah.
scene, right? So if instead of tracking the entire scene, if you just look at like the joint angles or velocities or orientation of the body, and then either look for anomalies on that, or you can look at it by like predicting the dynamics of that body. And then
Yeah, that can be one way of doing it. Uh, but I also learned that Kinect support is gone now, right? I think Microsoft is not providing Kinect anymore, so we may have to use the legacy Kinect systems. But going forward, I think this can be. But I think there may be other alternatives, and there are some open. Open source libraries to do this skeletal analysis. That can be one way of looking at it. Yeah, we haven't looked into that direction yet. Yeah.
So for this demo, it looks really nice. And how much sort of tuning of the parameters did you have to do, right? Because you have like number of layers, size of convolution kernels, all these like the hidden layer,
Yeah.
resizing images, and it seems like a ton of.
Oh yeah, it's unbelievable amount of. Yeah, I think for those who work in deep learning, it's a black art, that you learn over time. So I cannot tell you the secret. But if I were to tell the secret, there is no secret behind it. Actually, you have to. I think it's more by experience and using some rational sense of choosing in parameters. We did not do any optimization routine because we know it's going to be very hard. So for example, like what kind of activation functions you want to choose. So you want to choose 10H or ReLU or sigmoid. We tried few little bit and then we faced, oh, okay, everything will be ReLU. Now the image size, 64 by 64 or 32 by 32, we tried 96 by 96 also. But when we went to 3D convolution autoencoder, 96 by 96 was just, it would take not years, but maybe months or few days, at least weeks. So you have to, and then how many layers? Why 3? If you ask me why 3, I have no answer. It could be, but we realized that 3 layers were doing better than 1. But going more than 3 requires more computational resource. Maybe they are not useful, so it depends upon the application. So there are different, you're right, different parameters, and based on your sort of, so how many filters you want to learn? Why 16? Why not 32? These kind of questions. So the thing is, you try few things. That's what we did. We did not do any optimization, but we tried different combinations, and very early on we sort of freeze that, okay, we are not going to play around with this anymore because this. And you know what? Like if you are really fussy about these numbers, then it makes maybe it makes more sense to people like that. But I think if you use reasonable choices, then it doesn't matter much. Unless you want like your result to improve by 0.001%. I don't know. We haven't played around with a lot of parameters, but we know the difficulty. We have tried and used some heuristics. So one of the very famous paper on 3D ConvNet, they use three layers. So we just use that as our model. So these kind of things you can do.
So then, sort of, with what you have and the data you're using, do you think you're at the peak of what 3D Conv can do for all detection?
Yeah, for the thermal camera, yes. For the depth camera, I would say no. I think we could do better. It's actually interesting. So the data that we had initially, for some reason, the depth camera had a lot of black spots in the images. I don't know, was it the artifact of the, I'm not a vision guy, so I don't know, but I think there were a lot of black spots on the image, and that just ruined the accuracy, and we were wondering what happened. So one of the PhD students, he actually suggested that there is an algorithm to fill these holes, so why not you try that? And we just downloaded that code and we filled those sort of holes, those black spots, and the accuracy improved. So I think these are the challenges specific to a particular data, specific to what kind of thing. So I think there is, of course, there is improvement to improve. And as she asked, like what could be the threshold? So I think those are the bigger questions at this point for us. You were asking something else, right?
Yes, I'm not from the area, so I might be looking into this from a very different perspective. But there's some commercially available devices. You've probably heard of Google Solvi, which can detect very minute human movements. So do you see an impact of that? And the other question would be that how would the accuracy of your system compare with invasive technologies? Because when I was an undergrad, we used simple devices which could actually localize your cell phones using different access points. So I think some kind of physiological data you could get from very small devices which have some kind of electrical connectivity and wireless strength. So, and Bluetooth beacons in the environment could also work out. So if there are too many different sensing modalities, I believe that there is useful data that you could get and better results and better accuracy.
Yeah, I think that's a good point, and I think that's the right way to move forward to utilize as many sensing modalities that we can. So as I said, like the radars, depth cameras, if we can get some information, like I don't wear any watch or anything like that. I will not. Okay, but there are people who spend money and buy expensive watches, and Fitbit is people have no problem with that. So different people have different habits. Some people may want wearable things, some people don't. There are fall detection devices, so it's like you can wear it like a like a pendant. So if you fall down, then you can press the button. But sometimes you may fall down and it's so hard that you may just faint. You may never be able to press the button. So these are the questions. I think these are the bigger questions. So some modalities may work in some environment. Like so one of the criticism or shortcoming rather of vision devices is that they work inside the doors. If once you're outside, these cameras and they do not work anymore. So who is our target audience? We are probably targeting 80-year-old, 85-year-old, people who are mostly inside. So I think it depends upon what is your target audience, what kind of sensing modalities we can use, which are feasible or not. So you're right. If we can get some information about different types of data, it's pretty good. But my personal experience is that people don't like to be wired and everything. Doing all these things in a lab is great, but you don't want to walk on the street with 15 wires, attached to your body. And there are actually studies, and they show that people don't like to wear these kind of things. So that's one thing. I don't know about this Google thing. Sorry, what was that again?
So that's a radar. I also saw the video. I don't know about
okay.
complexities behind it. But what it does, Professor Brogan might know about it. So it could, Google.
Okay. I know that Microsoft used this radar kind of thing for some, finger recognition or. Oh yeah. So Microsoft was using it for gesture recognition. Yeah. So I think that could be an interesting thing to look forward. Yeah. Could be very similar to actually the radar that we are using, because these are low range radars, right? So for this radar that we purchased, we got not, I would say, the support, but we got access to the hardware, and so we got some MATLAB scripts as well. So we were able to program it, as sort of we wanted. So that is also helpful. But if you have a closed system, then you basically cannot do much with that. Yeah. Because I think these different sensors are looking things at from different point of view, and so it is I think very useful to combine these things, especially if we want to go in a real world setting where a person is in the house and then going out, and so you may need these kind of things which can complement each other.
Yeah.
Exactly.
That's always been our approach, is that this is just one way.
One way,
There's
yeah.
probably going to be a whole suite of ways.
Exactly. Yeah.
No one size fits all.
Exactly.
Yeah. Sure. Yeah.
Do you think in the future, these once you have radar
be a possible solution for detecting falls, say, in a mall or something like that, if it was integrated into security cameras? I mean, that would be way down the road, but do you think that's something that you could see?
Yeah, sure. Why not? I mean, but in crowded scenes, this is my understanding. In crowded scenes like airport, malls, and these kind of places where you have lots and lots of people, they still go the traditional way by looking at I think these cameras, because you do not have to sign a consent form to enter a mall that the government is going to monitor you anyway. So you have no choice, right? So I think because they want to see what's going on. Of course, we can use these kind of sensing modalities. Why not? But in these type of scenarios, I think the authorities may want to look at it. They make more sense when you're more concerned about the privacy and these kind of issues.